Welcome back. In this lecture, we're going to talk about Matroid duality and a number of different operations and their relationship with Matroid duality. So let's jump in and give the definition. Given a Matroid, that's defined as usual by its ground set E and its independent system I. We're going to define the dual Matroid as follows. M star is going to be defined on the same ground set, and I will denote its independent system by script I star, where this is such that some element I is in I star if and only if its complement is a base in I. So as an example of this, if I consider a graphic Matroid, so for G, a graph with nodes V and edges E, let's say this is a connected graph, then we know that some subset of these edges is an independent set of the dual Matroid. It's an independent set of M star, say subscript G, if and only if the complement of the edges is a base in the original graphic Matroid. In other words, if this is a spanning tree in the graph. So let's, first order of business is to check that M star is indeed a Matroid. So let's do that. I'll write this as a theorem. M star is a Matroid, and in particular, its rank function is given as follows. R star of S is equal to, S is any subset, the cardinality of S minus the rank of the full ground set minus R of E minus S. So let's prove this. Here's what we're going to do. First, we're going to show that R star, as I've given it, is the rank function of some Matroid. And we're going to do this using a result of previous lecture that shows that a rank function or a set function is a rank function if and only if its submodular R of the empty set is 0, and also that its marginal values are either 0 or 1. And we're going to just show this by direct computation. Actually, the only submodularity is the thing that we need to show. The other two properties are straightforward. So let's prove that part first, and then we're going to show that once we've shown that R star is indeed the rank function of a Matroid, we'll show that it is the rank function of M star. So what do we need to show? I need to show submodularity. So R star of S union T plus R star of S intersection T. My goal is to show that this is less than or equal to R star of S plus R star of T for any two subsets with potential intersection, any two subsets S and T. Okay, now, but by the definition, which is just sitting above, this is equal to S union T plus S intersection T minus twice R of E plus R of E minus S union T plus R of E minus S intersection t. And this is in turn equal to s plus t, because the cardinality of s union t plus the cardinality of s intersection t is just the cardinality of s plus the cardinality of t, minus 2r of e. That doesn't change. And now essentially this is a simple application of something like De Morgan. I've got, this is now the sum, I add the rank of e minus s and e minus t plus the rank of e minus s union e minus t. I'm keeping term by term. I'm writing term by term here. But now I have this relationship of intersection and union on the rank function r. We assume that r is indeed the rank function of the matroid M, and therefore we know it's submodular. So now I can apply submodularity, the submodularity inequality for r. So this is in turn upper bounded by s plus t minus 2r of e, nothing changed there, plus r of e minus s plus r of e minus t. But now you can see that just by reordering and by looking at this, this definition up top here, that this is exactly equal to r star of s plus r star of t. And that's what we wanted to show. So what have we done so far? Hence, r star is submodular. And I'll just write that, clearly r of the empty set is equal to 0. You can just check that from the definition. And also its marginal values are either 0 or 1. And therefore, r star is the rank function of a sub-matroid. So, in other words, let me call this m tilde. M tilde on the same ground set E, but with some independent system which I'll call I tilde, where I is an element of I tilde if and only if r star of I is equal to the cardinality of I is a matroid. This is what we have shown. And now we just need to show that actually this is the matroid that we wrote down up top. In other words, or on the previous slide, which is the dual matroid. So I need to show that that this matroid m tilde is in fact m star. So let's see how that works. So if I is a base of m star, that's the same as writing that r star of I is equal to the cardinality of I, which is equal to the cardinality, which is equal to the rank r star of E, which in turn is equivalent to r of the rank of E minus I equal to the rank of E. Note I'm using r now, not r star. And the cardinality of I is equal to the cardinality of E minus R of E, which is equivalent to saying that E minus I is a base of M. And therefore, we've shown that it has the right bases, and therefore this is exactly the polytope that we wanted to characterize. So now let's move to talking about two properties, or two operations that we can do on a matroid, deletion and contraction. So let M be my matroid. And let me define now these two operations. Deletion of an edge E, I'm calling it an edge, I really mean an element of the ground set, produces the following matroid, which we're going to denote in this way. And this is going to be the matroid on the ground set E minus E. And its independent system will be all I that are subsets of E minus E, such that I is an independent set in the original matroid. And then we're also going to define contraction with respect to, again, some element of the ground set. And this produces a different matroid, which we're going to denote by this. This is a matroid, again, on the same ground set, E minus E. But it's going to have a different independent system. Its independent system will be all E that are a subset of E minus E. But the condition that we need is that I plus E is an element of the is an independent set on the original matroid. And then the rank functions are defined in the following way. The rank in M with the deletion of an element E of some subset S is equal to the rank of S in the original matroid M for any S that's a subset of E minus E. That's all we need to define it. And for the contraction in the contracted matroid, the rank function is going to be the rank in the original matroid of S plus E minus the rank of the single element E in the contracted matroid for every subset of E minus E. So let's see a small example just to see that in fact these are different. So let's look at a graphical matroid, and so this is my graph, and let's call this the subset E. And now let's just look at what are the bases of with respect to contraction or with respect to deletion. So what are the bases of M with E contracted rather than deleted? So we're talking about which edges can we have. Now, I can't have this edge at all. That edge has been deleted. So we're just talking about what subsets of the other edges, and you can see that this is one base. I can't add another one. This is another. Another base. And another base. So to make it a little more clear. And what are the bases of M when I delete E? These are a little more straightforward, perhaps. Here's one. It's basically just any of the four spanning trees on these four nodes. And which one's left? This edge, this edge. So those are the four possibilities. So now let's see the relationship between deletion, contraction, and duality. And I'll write this in the form of a lemma. And it basically says that these are dual operations of each other. In other words, if I look at the contracted matroid and look at its dual, it is exactly equal to the dual matroid with the edge E just deleted. So let's give the proof of this. It falls into two cases. Case one is the setting where the rank of E is itself 0. So what does that mean? If the rank of E is 0, then it means that in M, no base of M contains this element E. So in this case, no base of M can contain E. But what does that mean about M star? Remember that in M star, we're looking at complements. Independent sets are complements of bases. So that means that every base, every maximal independent set in M star has to contain this element E. So that means that the bases of M with E contracted E, these are just the same as the bases of M, are the same as the bases of M. Again, because no basis of M contains E. And hence, these are the complements of bases of M star minus the set E. All right, let's look at now the second case, case 2. The only other case that we're going to consider is when the rank of the single element E is equal to 1. Now, what does it mean for I to be an independent set in an independent set in M in the dual of M contracted after I contract E and look at the dual? Well, this is exactly the same as saying that I is a subset of B for B some base. That has to be the case, which is the same as writing that I is a subset of E minus B prime, where B prime or B dash is a base of M contracted by E. This is by definition of duality, which is equivalent in turn to writing that I is a subset of E minus B double dash for a base B double dash that's equal to B dash plus E, a base of M, which is equivalent to writing that I is a subset of B triple dash for some base B triple dash of M star, where E is not an element of I. And therefore, this is exactly equivalent to writing that I is independent in M star with E deleted, which is exactly what we wanted to show. So let's summarize a few points on Matroid duality. So if I have M and M star, then contraction in M corresponds to deletion in M star. This is the content of the lemma on the previous slide that we just proved. And then in terms of some other definitions, a base in M is a complement of a base in M star. An independent set is the complement of a spanning set. not necessarily a base. And now there are a few other definitions that we had made in previous lectures. For example, a circuit is a minimal size dependent set. It's a set where if I remove any one of its elements, it becomes independent. And in M star, this corresponds to a cut, which we haven't yet defined. So I'll just define this now. This is a minimal set that intersects every base. And a loop, we mentioned, is a set, is an element that itself is not in I. In other words, an element E whose rank is equal to 0. And in the dual, this corresponds to a bridge, which is an element such that every base contains it. So implicitly, this previous proof broke down those two possibilities. Are we contracting a loop or not? And we saw on the previous slide, this was case 0, that if we're contracting a loop, then in the dual it is a bridge. Every base had to contain it. Okay, now finally, to wrap up this lecture, let's link it to our previous lecture when we defined the independent set polytope, and now we're going to define the spanning set polytope. In other words, let me define spanning set with respect to a matroid M. This is too long to write, so I'll just write PSS of M. This is the convex hull of all incidence vectors S, where S need not be independent, but it's a spanning set. S, a spanning set of E. And then let me define QSS to be equal to all vectors X that are component-wise between 0 and 1, and X of U is greater than or equal to the rank in M of E minus the rank of E minus U, and this holds for every subset U. So the theorem is that these two are in fact equal. PSS equals QSS, and again, it's easy to show one direction of this containment. So we're going to show the reverse. So let's let U be a subset of the ground set E, and let's suppose that this is spanning in M. And now we know that U is spanning in M if and only if its complement is independent in M star. We can just flip back to the previous slide and just see this correspondence between M and M star. Something is spanning if it's a complement of an independent set. Something's an independent set if and only if it's a complement of spanning in the dual matroid. So in other words, U is spanning if and only if E minus U, its complement, is independent in M star. This is just the definition. And thus, what does this tell us? It tells us that X is in PSS of M if and only if its complement, 1 minus X, and what I mean by 1 here is really the all ones vector, 1 minus X is in P independent set of M star. And therefore, this is the key that will allow us to use the results from the previous lecture. Because we know what it means for something to be an element of the independent set of any matroid, in this case, the matroid M star. And so, in other words, 1 minus X is an element of the independent set polytope of M star if and only if, the easy one, it has to be non-negative. And also it has to satisfy all of those rank constraints. And u minus x of u. Remember, what am I writing here? We needed x of u. I don't want to confuse you with notation. This is basically the sum of this vector over all the elements of a subset u. And so I'm going to pick up cardinality of u minus x of u. Okay, so this has to be less than or equal to, by definition here, of those constraints are m star of u for every u subset of the ground set. And now I'm going to plug in what r of m star is. In other words, we know that r of m star of u is equal to the cardinality of u plus rm of e minus u minus rm of e. This is, we basically derived this in our theorem on the duality of matroids. And now all I need to do is just plug this in to the right-hand side on the line above, and I get that x of u is, once I solve, so I'm going to move x of u over to the right-hand side, plug in for what r of m star is, and I'll get x of u is greater than u minus r of m star of u. Plugging in for r of m star, this is equal to u minus cardinality of u plus rm of e minus rm of e minus u. And that is exactly what we needed to show. So that concludes this result and our characterization of the spanning set polytope. And we will pick this up next time.